Hi there guys, welcome to today's recording. In this video we are going to go through the 2020 Aqueous examination paper 3.6, the one that the whole nation doesn't like and don't do so well in, but after this video you are going to do really well, hopefully. So leave a like if you enjoyed it, and smash the like button, subscribe if you haven't, and let's get into it. So the first question: an aqueous system contains a mixture of ammonium chloride and ammonia. So straight away you see NH4. So essentially what you have here, you have NH4 plus and you have NH3. You have the conjugate acid and the conjugate base, which means you have got a buffer. So even tells you have a buffer. So calculate the pH range of which is the solution is useful. So the pH range will be between 8.24 to 10.24. You may go, how do you know that? How the buffer works is that you want the pH range will be plus minus 1 of the pKa. Okay, so just remember that, very easy achieved trick here. And the next question is explain why add additional small amount of nitric acid to the buffer will not result in significant pH change. So remember, this is I did go through this really extensively in one of my explanation videos in the NCEA Level 3 Science Concept playlist, so maybe check that out if you're finding me to go through this a little bit too quick. But pretty much how buffer works is that you have NH3 and you have NH4 plus. This is the acids and this is the base, and when you're adding an acid or base into the buffer, they will neutralize it. Like say if I add HNO3, and this is where the NH3 comes in, like, hey, I don't like you, I am going to take away your hydrogen and I'm going to neutralize you. Okay, so it has neutralized it, and what happens here is that the NH4 plus will further dissociate and become NH3, and then you have made a small percentage of H3 or plus ions. Okay, so how the buffer solutions work is that the HNO3 is completely neutralized, and then it doesn't, the pH doesn't significantly change because the HNO3 which has a lot of H plus ions, but then all of that has been neutralized and turned into NH4 plus, and then the NH4 plus partially dissociate. If you look at that video that I did before, like say if I add it, I'll just talk about it here again if you can't be bothered going to that, but I really think you should. Let's say for example this plus H2O. Right, so if I have 100 H3O plus HNO3, that will dissociate into 100 H3O plus here. So if let's say if I have 1,000 of these, if I have 100 of these, can you see this 100 will completely get neutralized, and I'll make 100 of these guys. Yep, and I have 100 NH4 plus, and only 1% of that will dissociate, which will turn to 1 and 1. So as you can see, initially I added 100 units of H3O plus as an example, that numbers were made up, and then towards the end, only one of it fructified in the neutralization, survive after the neutralization process, and then actually dissociated and actually produce H3O plus ions, but that's not going to change the pH too much. Okay, so I think I've done the answers here. Yep. So the H3O plus from the HNO3 are neutralized, so they're removed by the base component. So the pH does not significantly change since the H3O plus are removed, and and then you produce a much weaker acid, which partially dissociate. Okay, so the equations are here. I didn't put the equation here because OneNote doesn't like equilibrium, so I just deleted it. All right, next one. Calculate the mass of NH4Cl that must be added to 200 ml of 0.5 mol per liter NH3 to give a buffer solution of pH 8.75. So, okay, assume there's no change in volume. All right. In 3.6, all the numbers that you see, so we see how many numbers? We see 1, 2, 3, 4. All of these numbers need to be used once. Okay, not twice, not 3 times, not 0 times, once. All of them will be used once. We don't give useless numbers in chemistry, and we don't expect you to use them more than once, because we're not doing math, we're not doing physics, we're just focusing on the chemistry aspects. We don't want it to turn into a contest of mathematics. Okay, so how this works, so first thing first, you need to remember the equation. You need to remember pH equals pKa plus log base over acid. Okay, so this is one of the equations you need to remember. And now first thing first, let's actually get the pH. pH equals 8.75, which is right here. pKa is 9.24, which is in the equation. I can't be, if you reverse back, you can find it in the equation. Plus log base base. Which one's the base? So what are we calculating? We're calculating the NH4Cl. So we have NH4 plus, and here we have NH3. And just take 5 seconds, pause the video, and actually tell me which one of the two is the acid, which one of the two is the base. Okay, so I won't spoil that. So quickly think. Pause if you need to think about it. This is going to be acid, this is going to be base. So we know what the acid concentration, we know NH3. NH3 is here, 0.05. So we don't know the we know the base concentration is 0.05 divided by X. We don't know what NH4 plus is. Okay, so, and this is just algebra, and that's not even hard algebra. So 8.75 minus 9.24, which is negative 0.49, which equals log 0.05 x. This is where you want to press, on my calculator, you shift log, and then you shift log this side, you shift log both sides. So that means, so on my calculator, I press shift log negative 0.49, which equals 0.324 equals 0.05 divided by x. So shift log just means you get rid of the log, and x equals, you move that to that side. So that's going to equal to 0.05 divided by the answer, which is going to be 0.154, lies 155, round to 3 significant figures, 0.155 moles per liter. Now we're not done here. Again, any of the mathematical parts, if you're struggling with that, please send an email to your maths teacher. You're here to learn chemistry. Now for the NH4Cl part, if you got the moles per liter, and you're wanting to calculate the mass, so remember mass equals N equals small m divided by big M. So we know the molar mass, which is always given. We need the mole. Now how do we get the mole? And mole equals N equals CV. So what do we know? We know the C, which is right here. This is the thing we calculated, moles per liter. We need the volume. They gave us 200 mils. They said assume there's no change in volume, so that means there's still only 200 mils of the stuff in there. So this is just going to be 0.155 times 0.2 liters, which is going to be times that by 2, which is going to be, remember, don't delete numbers from your calculator. Use every single digit from your calculator. Oops, I forgot a 0 right here. Moles. So this is how many moles you have. So mass equals your mole times the big M, which is 0.0309 times 53.5, which is going to give you 1.65 grams. Okay, so any of the buffer calculation, this is what I would strongly recommend you to do. You look at the question, figure out what equation to use, write the equation down, and then start substituting numbers in, and then you will just follow the steps, and then because you just need to understand what these things stand for, substitute it in, work it out properly, and once you get to here, you probably already got a merit, maybe, if you at least an achieved. Like say, even if you already just wrote this down, so the equation down, and then you attempted the substitution, you are getting achieved. And then if you can get to the x, and then somehow made some mistakes in the calculation, you can still get a merit. So it's not really that difficult. Okay. Next part, explain whether the buffer is more effective against, this is actually one of the questions that we talked about before. Is it better against an acid or base? So if we look at the question, where's the pH? pH is 8.75. So pH equals 8.75. That's the thing that we get given in the previous part. That's up here. And then we know the pKa is 9.24. So your pH, whenever your pH is smaller than pKa, that means you have more acid than base in the buffer. Why is that? Because pH equals pKa plus log base over acid. Okay, so what that means is that if your pH is smaller than pKa, So if your pH is smaller than pK, that means the size is going to be a negative number, and that means your base divided by acid is going to be a number smaller than 1. But that's just mathematics. Just remember that whenever your pH is smaller than pK, you have more acid than base. That means it's obviously more effective against a strong base because there's more acid in there. Okay, so let's just scroll down to the answers. All of these are explained very, very detailed in my tutorial video. So you know, in the playlist, level 3 science, level 3 chemistry concepts. So if because you know, I do need to be wary of time, because I don't want to spend an hour doing each of these exam papers when I have already gone through most of the concepts elsewhere. So just check out all the videos, check out the 2019 2018 exam videos, because it's all repetitive. Once you've done one exam paper, you are going to be pretty confident, because you will do the other exam papers like, hey, I've done this 20 minutes ago, it's the same question. Okay, so it's not that difficult. All right, next part. So solution equal concentration. So we know these are equal concentrations where HBr, CH3, NH2, NH4Cl. Rank the solution in order of the decreasing pH. So which one has the highest pH? So this, let's just look at the equation first. All right, so HBr, sorry, let me just change something really quick. HBr is a pretty decent strong acid. So this will completely dissociate. And then Br minus plus H3O plus. I'll just go through this question first, and then we'll talk about it. CH3NH2 is a weak base. That means it's going to accept a proton and then make that. And the next one is NH4Cl, which first dissolves into NH4 plus Cl minus, and then the NH4 plus. The NH4 plus will further dissociate into NH3 and H3O plus. Okay, so the first 1, 2, 3, the 3 species are given right here. Number 1 is a strong acid. Number 2 is because it completely dissociates, it makes tons of that, so it was a strong acid. Number 2 is a weak base, so you have some OH minus, so this is a weak base. And number 3 is a salt, so you have to dissolve that first into the NH4 plus and Cl minus ions. I mean, look at the you have 2 ions combined together. Separate them first, and then you're going to see the NH4 plus partially dissociate to form NH3. It's the couples. Now you would have seen the couples so many times from level 2. You would have seen them so many times in level 3. So just, you know, any amines, they're weak base. Like this is, you did that in level 2 organics. Like I shouldn't need to spend too much time explaining why this is a weak base here. Okay. Now NH4 plus turning into that, so this is a weak acid. So ranking decreasing pH, so that will be the highest pH is CH3NH2. The next one is going to be NH4Cl. The next one is going to be HBr. Okay, so relative concentration. So HBr has the highest concentration, completely dissociate. Whereas the second one, which is NH4Cl, this is a weak acid which partially dissociate into some H3O plus ions, and then the last one is a base. Okay, so you know, this particular question has quite a bit of if you want to look at the answers, is quite long. I couldn't be bothered writing all of that. Just remember that this is pretty much relevant to level 2. You just need to be able to write down the equation, identify which one's a strong acid, weak acid. HBr may be a little bit tricky, and I do actually want to spend a couple of minutes here. Is that, you know how with your periodic table you have F, Cl, Br here, and then I have iodine down here. These are the group 17 elements. The further down you go, the stronger the acid. Okay, so that means HF is actually a weak acid. Okay, it's actually a weak acid. And why is that? Because the F, now this is relevant to your 3.4. Remember, F is the most electronegative element. That means it really wants to bond to the hydrogen. So that's why it's going to be a weak acid, because it doesn't want to let it go. Okay, so as the electronegativity decreases as you go down the group, the chlorine becomes less electronegative, the Br becomes less electronegative, so they are more open to let the H go, so they tend to be stronger acids in that regard. Okay, so hopefully this makes sense. Move on to the next one. If the NH4 solution has a pH, oh, this is just easy, NH4Cl, you know, just again, let's just break it down, NH4 plus Cl minus, and then your NH4 partially, you don't need to write this again, I'm just showing you again. This is a weak acid, yeah, it's a weak acid. So what's a weak acid calculation? This is where you use the equation, memorize it, use it. H3O plus equals to the concentration, equals to Ka times the concentration of the acid. And in this case, we know the pH. So pH equals 4.70. So that means H3O plus is going to equal to the 10 to the power of negative pH. So what is that? 10 to the power of negative 4.7, which is going to be 1.99, so 2.00 times 10 to the power of negative 5. So this is 2.00 times 10 to the power of negative 5. And please tell me I can find the Ka somewhere. Oh, don't tell me it's all the way up here. Ka of NH4 plus is 5.75 times 10 to the power negative 10. Really, you just can't leave it down here, can you? That's so mean. That's so mean. 5.75 times 10 to the power of negative 10 times the concentration of the acid. So I shouldn't have scrolled up that much to find the Ka. Come on. So substitute. So we want to square this side, get rid of the square root. So this is going to be, oops, I shouldn't have done that. 10 to the power negative 4.7 squared, which is 3.98 times 10 to the power negative 10, which equals to 5.75 times 10 to the power negative 10 times the concentration of the acid. So the concentration of the acid is going to be this number divided by this number, which is going to be 5.75 exponential negative 10, and that will be 0.692 moles per liter. And I just looked at the answers, and the equation they gave them is incredibly short. So if you didn't know what you were doing and you were counting on the answer schedule to tell you how the answer came about, I'm pretty sure you are going to fail miserably, because it's not your fault. The answer schedule is not for you, it's for the teachers. So we don't need this many steps to understand what the heck is going on, but sometimes you do, and that's why I'm doing these. All right, question number 2. Write the equation for the equilibrium occurring in a saturated solution. So when you see this section, when you see Ks saturated, that means you are looking at solubility. So PbBr2 will dissolve in water to produce Pb2 plus ions and Br minus ions, and you need 2 of these. This is aqueous. This is aqueous, this is solids. Write the expression Ks equals Pb2 plus times Br minus squared. All right, you don't include solid in here. Now calculate the solubility. So this is just Ks equals 4x cubed, and you know, how do you know that? Because this is a 1 to 2 mole ratio. So Ks equals 4x cubed, and x is solubility, so equals 2.10 times 10 to the power negative 6. So x cubed equals, oh, you'll be surprised how many year 13 still don't know how to do this particular equation. Divided by 4 first, 5.25 times 10 to the power negative 6, and then cube root that number. So x equals, where's my cube root? There it is, and that will be 8.06, lies 8.07. 8.07 times 10 to the power negative 3 moles per liter. Make sure solubility has a unit of moles per liter. Next one. Determine whether precipitate. Yay, determine. So this is an excellent question. Determine the precipitate of the lead bromide formed with 125 mils added to 175. Okay, so we need the Ks. We need the Ks of lead PbBr2. It's right here. Yeah. So let's just borrow that. Ks PbBr2 equals 2.10 times 10 to the power of -6. Okay, so this is the you know, you refer to my videos for more detailed explanations, but I'm just going to talk about it again. But this is what happens if you have, this is what's happening here. You have lead nitrate, which is PbNO32, which is made of Pb2 plus and NO3 minus ions. And then you have this other couple, which is MgBr2, and then which separates into Mg2 plus and Br minus. So this is what I often talk about, because you know, as year 13s, one thing that you guys get to go to is the school ball. So imagine the left hand side, this is a couple, this is a couple, this couple Pb2 plus and NO3 minus, this couple is Mg2 plus Br minus, and they're pretty happy when they went into the ball. And the question is asking you whether, as they leave the ball, are we going to have Pb2 plus, which dumps NO3 minus, which then go hang out with the Br minus, who dumps Mg2 plus. That's essentially what the question is asking you. Is that going to happen? And so the interest, the thing of interest that we need to know how many Pb2 plus ions there are, and we need to know how many Br minus ions there are. And this is where we need to compare what we call the ionic product versus the solubility constant. Okay, now what's ionic products? You know, as year 13s, a lot of you you know, don't have to be from Auckland. I understand quite a few of my subscribers are from Christchurch and Wellington, and some schools I've never heard of. Hi guys. But the think of this, yeah. So if you're year 13 and if you want to get into a course at university, one thing that you need to get, especially I know in fact in the University of Auckland, they have a thing called rank score. So what that is that they essentially calculate your credits and then they give you a score. So what that means is that you need to, everyone's rank score is calculated the same way. So you can think this is your rank score or your GPA or your grades or whatever, you know, GPA, whatever the thing your school wants to, you know, inform you how you did for your school. So for your schoolwork, so this is your score, and this is your rank score, this is your GPA, this is the standard that the university has for all of the students that want to come to this school, come to the university. And what is ionic product? Ionic product is each individual score. So you know, everyone's score is going to be different because every reaction is different, if you think about it that way. So the question is asking you, for this particular student who got this grade, this grade, this grade for this 4 or 5 subjects, can this person come to the University of Waikato, for example? And then we compare this individual score versus the rank score. If it beats it, yay, you get to leave, you precipitate out, graduate, bye-bye. And then if you don't meet it, you stay in for another year. That's how you can interpret it. So the way of calculating IP, ionic product, and the way of calculating the KS is exactly the same. So if we look at KS here, let's go back to the question. The KS for this calculation is going to be calculated, you know, we did this for the previous question. This is how we calculate KS, and this is exactly how we calculate ionic product, because it would be unfair if, let's say, for Auckland students they calculate the grades in one way, for Canterbury students they calculate the grades in another method. That wouldn't be very, very fair, would it? Okay, so this is what we will need to understand. So we need two things. We need this concentration, we need this concentration. But these numbers have already been given here. You can see that when we add 125 mils of this lead nitrate and then the 175 mils of this magnesium bromide, and remember what I said about 5-10 minutes ago, every single number that we give you in chemistry will be used once. Okay, so you will need to use all of those numbers I highlighted once. So what does that mean? We need the Pb2 plus concentration. Yeah, so what was it before? Here it is, PbNO32, the concentration was 0.0365. And then if you, oops, ran out of space, that's okay. If you look at the other one, the Br minus, which is in here, magnesium bromide, this is actually a really tricky one. Let me show you where that number came from. Oops, MgBr2 it splits into Mg2 plus and 2Br minus. Okay, so what is the concentration? This concentration is 0. Let's not use that first. Can you guys see if I use X amount of this, that breaks down, I'll make X amount of this, and I'll make 2x amount of this, because this is twice as many moles compared to MgBr2. So for every single MgBr2 that breaks, I will make 2 moles of Br minus. So if this is 0.00262, this is going to be 0.0262 times 2. Okay, why didn't I need to do it here? Because for PbNO3, 2, this splits into Pb2 plus and 2NO3 minus. I don't care about that, I just want Pb2 plus, so this is 1 to 1, so I can just use a number. But for this one, it has to be 0.00262 times 2. Alright, now we're not done here, because remember, every number we need to use once. The solution has been diluted, because for my Pb2 plus it used to be 125 mils, but now I have mixed 125 with 175, which gives me 300 mils. Okay, so this is the H125 is my initial volume, the 300 is a new total volume. So same with the other one, it used to be 175, but now it is 100. So now it is 300. So once you've done these two calculations, you'll find that this top equation is going to be, the top concentration is 1.52 times 10 to the power negative 2. The bottom concentration will be 3.06 times 10 to the power negative 3. Okay, now we are going to substitute these numbers into this particular equation. So I'm just going to clear a bit of space. I'm just going to rub out all of these. Going to make a bit of space, because otherwise no space down there. So on my ion product is going to be 1.52 times 10 to the power negative 2 multiplied by 3.06 times 10 to the power negative 3 squared, which equal to 1.42 times 10 to the power negative 7. Now you compare your IP versus Ks. You can see your IP is smaller than Ks. You are not going to graduate from your high school. You have no precipitate. Okay, so there you go. That's the explanation for this particular question. As you can see, it's went on for a bit longer. But like I said, I probably said this too many times. Refer to my other videos if you look at the older concepts where I spend a bit more time going through these. If you find me going through this a little bit too fast. Hopefully I'm not going this too fast. All right. Now next one, explain the effect of adding the solubility of nickel hydroxide. So something started from last year that you actually get given the complex ion formations, the complex ion, sorry. So on your sheet, on your resource sheet, you'll find this. One of the things that has nickel on it is has nickel in it is this particular complex ion. This is in the resource sheet. Okay, so you have nickel, you have NH3. So obviously it's this bad boy. Okay, so this is the equation that you need to think about. You have nickel hydroxide, which then partially dissolves into these two things. But then if you add ammonia, what's going to happen is that the Ni2 plus will react with the added ammonia to form this complex ion. So you don't need to memorize what it forms, because that's already been given to you. You just need to understand that you just need to be on high alert that you are going to see the complex ion formation. So why does the solubility increase? So the solubility will increase. Why does that? Because normally if I dissolve the sodium hydroxide, the nickel hydroxide in water, it's just going to do the top half of the equilibrium. But what happens in this case, if you dissolve the ammonia, the Ni2 plus will react with the ammonia to form this guy. So as a result, the Ni2 plus concentration, is going to decrease. If it decreases, the equilibrium here is not at equilibrium anymore. What does that do? It's going to shift to the right to make more Ni2 plus. And therefore solubility will increase. Okay, so hopefully that makes sense. I think I put it here. So this is the top half of the answers. This is the equation. So when you add it in, the Ni2 plus are removed because they form a complex sign. To re-establish equilibrium, you shift to the right to make more Ni2 plus, therefore solubility increases. So that's the first half of the answer. Now, if the pH is decreased below 4, let's go back to here again. Nickel hydroxide turning into Ni plus, 2 plus, and 2 OH minuses. So what's going to happen if you do a pH below 4? So what does pH below 4 has? This is an acid. And what do acids have in common? They have lots of H3O plus ions. And you may go, hold on a minute. So this is not a complex ion formation. Oops. This is a not a complex ion formation. You have an acid and you have a base. Neutralize. Okay, so the H3O plus will neutralize, or neutralize some of the OH minus. So this, OH plus. So this concentration will decrease. What does that mean? The equilibrium will shift to the right to make more OH minuses. And therefore solubility decreases because you're shifting to the right. So which is the bottom half of the answers here. When the TH is below is decreased below 4, the H3O plus remove the OH minus ions because you form water, and to restore equilibrium you shift to the right to dissolve more, to make more OH minus ions. Okay, so hopefully that makes sense. One more question to go, and this is all calculation, I believe. Yeah, nope, still not done with this question here. Calculate the solubility of a saturated solution of nickel hydroxide at pH 8.25. Okay, so we know a few things here. So Ks is this. So Ks is calculated using Ni2 plus multiplied by OH minus to the power of 2. So what are we calculating? Calculate the solubility of a saturated solution. So we want to know X. Okay, so we want to make solubility X, but then this is pH equals 8.25. So what does that mean? pH equals 8.25. We can use this number to actually calculate the OH minus concentration. So this is a common ion question. Okay, so this is a common ion because you are dissolving this, which has the OH minus ions as a product. You're dissolving it in a base which has a common ion of the OH minus, so we can actually calculate what this is. How do we calculate it? If pH equals 8.25, that means OH equals, I'm doing this on the internet, so I better not do it wrong. This is 5.75. That means we can calculate the OH minus concentration by using 10 to the power of negative 5.75. 10 to the power of negative 5.75, and the answer is 1.78 times 10 to the power of negative 6 moles per liter. That is a 6. Okay, so this is what we do. So we know Ni2 plus multiplied by the OH minus. You just substitute it in here. You just substitute this guy in here, which is 1. Oops, I'm going to write that with the highlighter. 1.78 times 10 to the power of negative 6 equals Ks, which is 6 times 10 to the power of negative 16. Solve that in Ni2 plus. Oops, I forgot the squared. Solve that and Ni2 plus will be 1.90 times 10 to the power of negative 4 moles per liter. So this is a common ion effect question. So if you're trying to dissolve something in the solution that has the same ion in it, you don't go, this is X, this is 2X. Well, no, because this OH minus is no longer twice as many as X, because you're dissolving it in a solution that already is a basic, so that can't be right. So you just have to assume. That's why we calculated the hydroxide ion concentration, which is what we did here, and you just substitute that in there. You got the Ks, you got the OH minus, so solve it Ni2 plus, which is the solubility. Okay, because it's 1-to-1, no ratio. Oh, question number 3. How are we going? 35 minutes. Oh god, this is going to be a long one, boys. But here we go. Let's go now. List all the species. So this is a titration curve. Let's look at it. 0.28 moles per liter HCl to 25 mils of this. So we need to know this. pK is that, K is that, and they gave the equation. Thank you very much. List all the species in solution of sodium ethanoate. Oh god, that's just too easy. So Na, this is just CH3COO-Na. So remember, this is what we're wanting to do, to separate that into the ions, and then hopefully understand that this guy partially dissociate into the into the conjugate acid, which is this. Okay, so what are the species? I'm just going to highlight them. You don't have any of these left because they have completely dissolved. So you have this, 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 and don't forget, in every single solution, so let's just write them down, you have lots of this, you have Na+, you have CH3COOH, which is in very small concentration, you have OH-, which is in very small concentration, and H3O+, which is in a very tiny concentration. Okay, next one, calculate the pH. So this is the first point of interest. This is looking at before any titration has occurred. So you're looking at sodium ethanoate concentration. So you're just doing this part pretty much. You're doing this is a weak base calculation. So you just go H3O+ equals Ka times Kw divided by the concentration of the base. Just to substitute Ka, what's Ka again? Let's scroll up. 1.74 times 10 to the power negative 5, 1.74 times 10 to the power negative 5, multiplied by 1 times 10 to the power negative 14. You just substitute the numbers, divided by the base, which is right here, 0.224, 0.224. Therefore, H3O+ concentration, you can crunch those numbers in your calculator. You should get where is it? 8.81 times 10 to the power of negative 10. And again, I'm just looking at the answers on the NCEA website. Good luck trying to figure that out yourself, guys. It doesn't do that well of a job for you. So negative log that is 9.05. Just remember this equation, you know. So first thing first, we identify it's a weak base. How do we identify it's a weak base? Because we did the equilibrium up here. You can see this OH- sign, so this is a weak base because it partially dissociated. And then you just write the numbers, write the equation down, look for the numbers, substitute it, and prepare to get a merit. Next one, why are hydrochloric acid and sodium ethanoate both good electrical conductors? What is that? That's NCEA level 2. What is that question doing here? Why is that good? So HCl, I'm just going to right it here. HCl is a strong acid, so that means it completely dissociate. You have lots of the free moving ions sitting here. Great electrical conductor. Sodium ethanoate. So this is a great conductor because it dissolves into water. Dissolves in water first. So you have lots of the free moving ions here, which means they are really good conductor. Okay, so you can look at the answers here. So the conductivity depends on the concentration of free moving ions. HCl is a strong acid, completely dissociate, loss of Cl- and H3O+, therefore it's a good conductor. Sodium ethanoate, it dissolves, completely dissolves, produces Na+ and CH3CO-. So, you know, high concentration of free moving ions, high electrical conductivity. Now, next one, calculate the pH at equivalence point. Oh Lord, I need all of these concentrations. I'm just gonna copy this. Can I just copy this? Yes. Copy and paste. Yes, genius. The master, the legend of copy pasting. You know, that's gonna work you well for level 2, level 3 organic. Now, calculate the pH at equivalence point. So, they have given you, now I'm gonna, should I show you the long way? I'm just gonna cheat a little bit. Should I cheat a little bit? They gave you the thing here, it's 15, but I'm just gonna, actually, let's just do it my way, all right? So calculate the pH at equivalence point. So this is where I'm just going to borrow the equation because I need more space. Oops. So this is a neutralization reaction. Now we know these things. We know that there's 25 mils, which is 0.025 liters. We know the concentration, which is 0.224. We know the mole that we started with. N equals CV, just multiply them together. Because if you, again, I'm just showing you the method that will work for any equations in buffer as well as pH at equivalence point, 5.6 times 10 to the power negative 3. Now at equivalence point, these 2 moles, let's not do that. At the equivalence point, the 2 things I'm highlighting, the moles are the same amount. So this is also going to be 5.6 times 10 to the power negative 3. Because at equivalence point, that means they neutralize each other completely. We know the concentration is 0.280. We know the volume is going to be N divided by C, which is 5.6 times 10 to the power negative 3 divided by 0.280, and that's going to equal to 0.02. Oh, good thing I didn't use that 15 up there. 0.02 liters. Okay, so why do we do all this? So this is before anything. So this is before titration. And once we have neutralized them, this is going to be 0. This is going to be 0 because they neutralize each other. They're gone. And then this mole is going to be 5.6 times 10 to the power negative 3, because it requires 1 mole of this and 1 mole of this to make 1 mole of this. So that's why this is gone, this is gone. Then you produced 5.6 times 10 to the power negative 3 moles of CH3COOH. So because at equivalence point, you don't have CH3CONA and HCl anymore. They're gone, they're neutralized. You have made CH3COH, which is a weak acid. It will partially dissociate into CH3CO minus. So if you look at this equation, this is a weak acid. This is a weak acid. So what we need to do, we just need to calculate, we just need to use the equation H3O plus when you have the weak acid equals the Ka times the concentration of the acid. Okay, so what's Ka? Ka was, oh Lord, 1.74. 1.74 times 10 to the power of negative 5 times the concentration of the acid. Now, remember the number that we calculated is the mole amount. Yeah, this is how many we're dealing with moles. To find this concentration, we need to go and C equals N divided by V, which is 5.6 times 10 to the power negative 3 divided by the total volume at this stage. This is why we did this. We got this number from the question, and that's why we did this calculation at the end. So we have 45 mils. Okay, so it was 25 at the beginning. I added 0.02 mils to completely neutralize. So this is going to be 0.045, which is going to be 5.6 times 10 to the power negative 3 divided by 0.045, and that's going to be 0.124 moles per liter. And if you multiply this by 1.74 exponential negative 5, square root this number, you should get 1.47 times 10 to the power negative 3 moles per liter for your H3O plus concentration. And that means your pH is going to be negative log 1.47 times 10 to the power negative 3, and that's going to be 2.83. Okay, so it's a bit of a long one, but again, have a look at the, I'm just going to drag this down a little bit, have a look at the more detailed explanation that I did for the what do you call it, for this particular part. Okay, so I copied this thing in. This is the last question. Yay. How long is this video going to be? Let me have a quick look. It's turning into 45 minutes. Oh god, you guys are gonna have fun. In the second titration, so we have 25 mils of 0.224 titrated with the same 0.828 mole per liter. So if you look at everything, it's exactly the same. Okay, so this is copy and paste. This is the original question. This is the original question. So this is not part of the question. Okay, this I just copy and pasted it just so you can have a look at it. The only thing that has changed is that we change the species. Can you see that Ka? And then this Ka. This tells you that, well, they saved it here. I actually didn't need to copy paste it. It's just deleted so you don't get confused what the heck that is. Let's just like this whole thing. Let's delete it. Okay. So everything is exactly the same, except this time you have used 2.29 times 10 to the power negative 11 instead of the original 1.74 times 10 to the power of negative 5. Just get that straight here. CH3 NH3 plus has a Ka which is smaller than CH3COOH. Okay, so this Ka is smaller. So that means this guy dissociates less, because what does Ka mean? Ka means the standard dissociation of the acid. So this is a weaker acid. Okay, so this is a weak acid because it has a lower Ka. Now at equivalence point, you will produce, we will make CH3 NH3 plus, which we know is a weaker acid, which we know if it's a weaker acid, there is less H3O plus ions being produced. That means you will have a higher pH. So you should select higher pH. Okay. So here it goes. So at equivalence point, because at equivalence point you only have the weak acid, like in this case, you know, CH3COOH, CH3NH3 plus. Okay, so in both scenarios, you know, in the first scenario you get this one, the second scenario you get that one. Because this has a smaller Ka, which means it's a weak acid, therefore it dissociates less, therefore it has less H3O plus, therefore pH will be a little bit higher. Okay, so this video is already much longer than I expected it to be. It's just quicker. Like if I was answering these exams, doing the questions for the exams, I'll probably be done in 25 minutes. But instead, I'm doing 20. How long is this now? Turning to 450 minutes. But yeah, this is the level 3 Aqueous exam. Hopefully, you've been finding it okay. And yeah, leave a like, subscribe if you haven't, and I'll see you guys next time. Bye bye.